Okay, so hi guys, in this lecture we will be comparing stability between two compounds based on our priority rule, which is called ARI. Okay, so let us start. Okay, so we'll be continuing on comparing stability. Okay, so let's compare the stability order between okay and this one. Okay, so please remember the order of comparison, which is called AE or HI. Okay, so what would be the order between the two? As you may know that both are aromatic. Why? Because the lone pair of nitrogen and oxygen are involved in the ring, so no doubt on that. So second, uh, let us compare the equivalent RS conditions. So N will have positive charge on it and O will have positive charge on it. Both have equal amount of covalent bonds. Both have complete octet. But the third one, that nitrogen will have, sorry, oxygen will have positive charge. So more electronegative element is having positive charge on it, hence positive charge on nitrogen is slightly more stable, hence one is more stable than two. Okay, let us compare on this. If we have something like this and this, so both are aromatic. So regarding equivalent RS, nitrogen will have a slight positive charge because of the lone pair donation within the ring, hence the first compound will win on the E condition. So by equivalent RS condition, one is more stable than two, as in two positive charge would be there, so it would be leading to some charges in the compound. On the other hand, there are no charges in the resonating structure. Okay, so one is more stable than two. Third point is we have this and we have this. Okay, so in the first case we can see this is aromatic, this is not aromatic. So based on aromaticity, which was the first priority rule, first one is more stable than two. Okay, let's look at the fourth one. We have something like this and this. So which is more stable? Obviously this one. Why? This is aromatic. So based on the first rule that you have to check for the aromaticity first, this is more stable. Okay, we have to check between this compound and this compound. So how do we check? Both are not aromatic, both are non-aromatic, so let's skip that. Regarding equivalent RS, so let us see. So number of covalent bonds remains the same in both the cases. which are 3, and number of negative charge also. uh, Both compounds have field octet of all the atoms, especially electronegative elements or atoms. One structure for this would be something like this, and for this would be something like one second. This would be a positive charge here, right? Okay. So its resonating structure would be something like this. So it would be having positive charge, and this one. Okay. So this would be the resonating structure for these two compounds. So number of octets are filled. Most electronegative element should be having negative charge, which is having it. So equivalent RS is also not the situation here. So the third is resonating structures. So in resonating structures also, uh, so in resonating structures also means both of them are having resonance. So it is also an auto comparison, but you can see that for this compound we are having a extended resonance, and for this compound we are having a cross resonance. So what can we say? That this, for this compound we are having, means this is the type of resonance, and for this compound we are having, this is the type of resonance. So this would be more preferred over this based on resonating structures. This is more stable. Okay, let us look at some more example. We in this example we need to compare the heat of hydrogenation. So heat of hydrogenation is inversely proportional to the stability. Okay, more the number of more the number of bonds, more is the heat of hydrogenation. Now in this case, ideally the order should be more the number of covalent bonds, more is the heat of hydrogenation. Like this, 2 1 3, but on the contrary we find the order is 1 2 and 3. Why? Because as the number of covalent bonds are increasing in this case, you should also notice that it is gaining aromaticity, and it is a most stable compound among all the three, right? Because both these two are non-aromatic. So hence, because this compound gains aromaticity, it would be less stable than the first compound. Hence, ideally the order should be 2 should be greater than 1, but as second gains aromaticity, the 1 should be having less lit of hydrogenation than the first compound. Okay, so if we compare this on an energy level, this is our single bond for which heat of hydrogenation was 120 kilojoule per mole. This was our two double bonds for which heat of hydrogenation was 232 kilojoule per mole, and this was our benzene structure. whose heat of hydrogenation was not 232, not 120, but 208 kilojoule per mole. So this is less than 2 double bonds, which is because of due to aromaticity. Okay, so I hope you follow up with this thing. Okay, so in the next lecture, okay, we'll be talking about the plus M and minus M effect, but to just set the tone right for you, let me give some general knowledge to you. So suppose this is a benzene ring and it has OH group attached to it. Then as O will be donating its electron in the phenyl ring for having some resonance or resonating structures, this group will be called plus M group. And on the other hand, due to inductive effect, this oxygen is more electronegative than this phenyl ring. Hence, the OH group would be having a minus I effect, right? On one hand, it is donating electrons for the phenyl ring for the resonating structures, and on the other hand, it is taking electrons due to electronegativity. So this is some fun fact about it, and let us take some another example. If we have some structures like this, so what is happening in this case? In this case, phenyl ring is acting as phenyl ring will be donating its pi electrons to form negative charge on oxygen. So in this case, phenyl ring is acting as plus M effect, and our C double bond O group is acting as minus M, and obviously it was minus I also because this is more electronegative than the phenyl ring. Okay, so see you in the next lecture.